the Big Bang Theory has faced new challenges with the latest discoveries made by the James Webb Space Telescope, which has provided groundbreaking insights that could reshape our understanding of a universe. A recent image captured by this telescope has generated significant discussion among experts, presenting compelling arguments that have surprised the scientific community and resolved long-standing debates about the nature of the cosmos. This visually stunning discovery is not just another astronomical observation, but has the potential to transform our perception of the universe. The latest image taken by the James Webb Space Telescope challenges some of our most fundamental assumptions, particularly regarding the age of the universe and its rate of expansion. These questions have puzzled scientists for generations, leading to extensive research and various hypotheses in search of definitive answers. Cosmologists dedicate their work to understanding how the universe originated, how it functions, how it has evolved over time, and ultimately how it will end. Over the last century, there have been significant advancements in this field. The Big Bang Theory, which remains the most widely accepted explanation for the origins of the universe, suggests that the cosmos has been expanding for approximately 13.8 billion years, beginning from an extremely hot and dense state. A key factor in measuring this expansion is the Hubble constant, which determines the rate at which the universe is growing. However, calculating this constant is far from straightforward, as two primary methods, local measurements and observations of the early universe, often yield different results. As scientists rely on specific celestial objects such as stars and typi supernova to serve as standard candles due to the predictable brightness. By measuring their distances, astronomers attempt to determine the Hubble constant. The expansion of the universe does not occur at a uniform rate, making it even more challenging to pinpoint an exact value. One approach involves studying the early universe through observations of the cosmic microwave background (CMB) radiation, a remnant from when the universe was only 380,000 years old. First detected in the 1960s, the CMBB provides valuable insights into the universe's age and expansion rate by analyzing tiny fluctuations in its temperature and polarization. However, a significant problem arises. These early universe measurements do not match local measurements. Data collected from nearby galaxies suggests that the universe is expanding faster than what CMB readings indicate. Scientists have been working tirelessly to resolve this discrepancy, as it suggests either an incomplete understanding of fundamental physics or potential errors in one or both methodologies. With the powerful capabilities of the James Webb Space Telescope, scientists can now peer deeper into space than ever before, revealing celestial objects and phenomena that were once thought impossible to detect. Researchers initially hoped that the telescope's data would help refine calculations of the Hubble constant, yet the first sets of findings have introduced unexpected inconsistencies. This new information challenges existing models and forces scientists to reconsider what they know about the nature of space. There is growing speculation that these discoveries could lead to the identification of previously unknown particles or forces, or even a re-evaluation of the concept of dark energy, an enigmatic force responsible for accelerating the universe's expansion. Scientific understanding of space has continuously evolved with each new discovery. For example, when the cosmic microwave background radiation was detected in 1965, it provided strong evidence for the Big Bang, challenging previous assumptions that the universe would expand indefinitely at a constant rate. Then, in the late 1990s observations revealed that the expansion of the universe was actually accelerating due to dark energy, a revelation that reshaped our understanding of cosmology. Every new finding forces scientists to test whether it aligns with existing theories, or if it necessitates a new framework to explain the universe's behavior. Without these challenges, the field of cosmology would stagnate rather than progress. One of the most intriguing aspects of the current cosmological debate is the concept of Hubble tension, which refers to the discrepancy between different measurements of the universe's expansion rate. This issue is closely linked to the distribution of matter in space, as variations in matter density across different regions help shape the large-scale structure of the universe. Some areas are densely populated with galaxies, while others are relatively empty. Scientists use various methods to study this distribution, including gravitational lensing, a phenomenon in which massive objects such as galaxy clusters bend and magnify light for more distant celestial bodies. This effect allows researchers to infer the presence of dark matter, a mysterious substance that does not emit light but influences the gravitational structure of the universe. Further analysis of the cosmic microwave background provides another avenue for understanding these cosmic irregularities. The light from the CMBB has traveled for about 13.8 billion years, carrying information from the early universe. However, there is an unresolved issue: the large-scale distribution of matter observed today does not match the uniformity suggested by CMB data. This discrepancy implies that there may be unknown factors influencing the structure of the universe. The non-uniform distribution of gravity suggests that the universe was more homogeneous in its early stages than what is currently observed through gravitational lensing. This inconsistency has led scientists to revisit theories about dark matter and its role in cosmic evolution. A research team led by Ree and his colleagues utilized the James Webb Space Telescope to investigate whether measurement errors in previous telescopic observations could be responsible for these inconsistencies. Their findings, however, only confirm the discrepancies, reinforcing the notion that there may be a fundamental flaw in our current understanding of the cosmos. In an interview with an astronomical magazine in the United States, Ree expressed concern that somewhere between these observations lies a critical gap in knowledge. The James Webb Space Telescope's ability to capture incredibly sharp and detailed images has enabled astronomers to study cosmic distances with unprecedented precision, yet instead of resolving uncertainties, it has introduced new questions about the nature of dark matter and dark energy. Both dark matter and dark energy remain among the greatest mysteries in physics. They are believed to comprise a significant portion of the universe, yet their true nature continues to elude scientists. While black holes have traditionally been considered the most likely explanation for certain gravitational anomalies, recent findings suggest that dark matter and dark energy might play a far more complex role in shaping the universe than previously thought. The growing body of evidence indicates that our current models may need to be revised, as they do not fully account for the intricate interactions governing cosmic expansion. The revelations brought forth by the James Webb Space Telescope emphasize the ever-evolving nature of scientific exploration. Each discovery presents new challenges and prompts scientists to refine their theories, leading to deeper insights into the universe. The unresolved discrepancies in cosmological measurements highlight the need for continued research and more sophisticated observational techniques. As technology advances and telescopes become even more powerful. The hope remains that these mysteries will eventually be unraveled. Until then, the pursuit of understanding the fundamental forces that shape our universe remains one of the most exciting and intellectually stimulating endeavors in modern science. The discoveries made by the James Webb Space Telescope (JWST) have provided some of the most striking challenges to our current understanding of the universe. While astronomers initially expected the telescope's observations to help resolve long-standing cosmological debates, its findings have instead introduced new uncertainties, forcing a re-evaluation of key aspects of the Big Bang theory, the debate over the universe's expansion, the role of dark matter and dark energy, and the inconsistencies in current measurements has led scientists to reconsider what they thought they knew about the cosmos. With its ability to observe distant galaxies with unprecedented clarity, the JWST has revealed new celestial structures and data that do not fully align with prior models, suggesting that something fundamental may be missing from our theories. One of the biggest unresolved questions in cosmology is the rate at which the universe is expanding. The Hubble constant, a key value used to measure this expansion, has been calculated using two different methods, one based on the cosmic microwave background (CMB) radiation from the early universe, and the other relying on local measurements of stars and galaxies. However, these two approaches produce conflicting results, a problem known as the Hubble tension. If the universe were expanding at the rate suggested by early universe data, it should appear slightly different when observed through local measurements. The fact that these two methods yield inconsistent numbers suggests that there might be unknown physics at play, or that existing models of cosmic expansion need revision. The JWST was expected to help resolve this issue by offering more precise measurements of distant objects, but instead it has deepened the mystery. Observations have revealed discrepancies in the distribution of matter across the universe, particularly in relation to dark matter and how it influences cosmic structures. Dark matter is an invisible substance that does not emit or reflect light, but its gravitational effects can be observed through phenomena like gravitational lensing. When massive objects like galaxy clusters bend the light from more distant galaxies, scientists can use these distortions to map the presence of dark matter. However, the new observations from the JWST suggest that the way dark matter is distributed in the universe does not match previous predictions, further complicating the Hubble tension problem. One possible explanation for these discrepancies is that the fundamental nature of dark matter is different from what scientists have assumed. Traditionally, dark matter has been thought to consist of weakly interacting massive particles, WIMPs, but the latest finding suggests that it might have additional properties that influence cosmic expansion. Another possibility is the dark energy, the mysterious force driving the accelerated expansion of the universe, may not behave the way current models predict. Dark energy is believed to make up roughly 68% of the universe, but its properties remain largely unknown. If dark energy has changed in strength over time or interacts differently with matter than previously assumed, it could explain some of the observed discrepancies. Ree and his team, who have been closely analyzing data from the JWST, were particularly interested in whether previous telescope observations contained errors that might explain the inconsistencies. However, their research only confirmed the deviation seen in earlier measurements, reinforcing the idea that there is a deeper issue with current cosmological models. In an interview with an astronomical magazine, Ray stated that Somewhere between these observations, there must be a fundamental flaw in our understanding of the universe. This statement highlights the growing realization that scientists may need to rethink some of the core principles of cosmology in addition to raising questions about dark matter and dark energy. The JWST observations have also challenged assumptions about galaxy formation and evolution. The telescope has captured images of galaxies that appear far more developed than expected, based on their estimated age. According to the Big Bang theory, the earliest galaxies should be relatively small and simple, gradually growing in size and complexity over billions of years. However, the JWST has detected massive, well-formed galaxies that appear to have existed when the universe was only a few 100 million years old. This contradicts previous models of galaxy evolution and suggests that either galaxies formed much faster than expected or that our understanding of the early universe is incomplete. One possible explanation for this phenomenon is that the initial conditions of the universe were different from what scientists have assumed. If the density of matter and energy was not as uniform as previously thought, then galaxies might have formed more rapidly in certain regions. Alternatively, there could be unknown processes at work that accelerated the formation of large-scale cosmic structures. These findings have led some researchers to propose modifications to the standard model of cosmology, including theories that incorporate new forms of matter or interactions that have not yet been discovered. The implications of these discoveries extend beyond cosmology and into fundamental physics. If the current models of dark matter and dark energy are incomplete, then scientists may need to develop new